problem 3.14 out of Griffiths' Introduction to Quantum Mechanics. Before I get into solving this problem, if you wouldn't mind please liking the video and subscribing, I'd greatly appreciate it. It's an easy and free way to support me, and I post a lot of solutions from undergraduate physics textbooks. So if you're interested in physics or you're studying physics, I think my channel has a lot to offer you. Now let's get into the problem. Basically, this problem is showing four different things to be true. So part A says show that the sum of two Hermitian operators is itself a Hermitian operator. In other words, sum of two Hermitian operators, which I'll call H1 and H2. We want to show that itself is also Hermitian. So this can be expressed just like this. And H1 and H2 by themselves are both Hermitian, which means I can write it like this. But then I can write this as now just one inner product, which is H1 plus H2 and F, G. But that's the definition of a Hermitian operator, so that satisfies what we're trying to show. Part B says, suppose Q is Hermitian, and A, or alpha, is a complex number. Under what condition on alpha is alpha Q hat Hermitian? So we have this operator, and alpha is some constant. We want to show, well, that equal sign might just be, there we go. So we can write this as, and what we want to do is show the condition where this is true. So we want to find out where that's the case. Well, from here, alpha is a constant, and it's in the ket, so that just comes out. And over here, this time alpha is in the bra, so when we pull it out, we have to take the complex conjugate of it. Okay. Now Q is Hermitian, so this can simply be written like this. But then notice that these are the same. So if you were to divide that out, alpha equals alpha star. That's just another way of saying that alpha is an element of the real numbers. Okay. Number C says, when is the product of two Hermitian operators Hermitian? So let's work through that. So we'll call them H1 and H2 again for the two Hermitian operators. And we want to find this condition where the product is also Hermitian. We want to find where that is true. Well, first off, H1 is Hermitian, so I can move that independently. H2 is also Hermitian, so that can come over here, no problem. Essentially, we're just doing it in 2 steps there. Hopefully, you're okay with that. So, the question is, when are these 2 equal? When is H1, H2, Fg equal to H2, H1, Fg? Clearly, that has to be when H1, H2 equals H2, H1. Okay. Moving on to part D. Show that the position operator and the Hermitian operator are both Hermitian. We'll start with the position operator. And just remember, the position operator is really easy. It's just equal to x. So then this inner product, if we were to write it in an integral form, the bra is complex conjugate times x times g of x dx. At the same time, this is equal to, again, it's an inner product, so it's defined very similarly. The only difference is now x is in the bra instead of the cat. But x doesn't have any imaginary component to it. So it's really no different than just this. And this is the exact same thing, which is the definition of Hermitian, since this equals this. Okay, so that was pretty straightforward. Now let's look at the Hamiltonian operator. It's a little bit more involved, but similar in practice. So let's find this inner product first. And it's defined the exact same way that we've been defining our inner product. Now what we're going to do is we're going to insert our Hamiltonian. So remember that p hat is equal to minus I h bar d by dx. So you can have this operate again. So p hat squared now on one hand the negatives cancel and you're left with I squared, which is negative 1. So you're going to be left with minus h bar squared divided by 2m, and in this case everything's only a function of x, so the partial derivative notation isn't really necessary. And then we have our v of x term out here, and then g of x dx. Okay, so let's see if we can simplify this. The first thing I want to mention is we're going to use a property we actually solved above, which is that if you add two individual Hermitian operators together, the sum of that is also Hermitian. Well, that's important because we have basically two, right? You can H hat is comprised of two separate operators, and if we show that each one is Hermitian, then the product is also Hermitian. So we'll start with the first part that I think is the easiest, which is that so this would just be this is just your v of x term. Okay. But v of x is not complex, so it's just a real number, it's some potential. So if we write it like this, this is the exact same thing as this. Okay, so these are equal. So your v of x term, this is good. That's clearly Hermitian. But what about this term? If we can show that that's Hermitian, then we can show that your Hamiltonian is as well. And that was the point of this whole, just making sure I properly read that. Okay, so now what we're going to do, and then we're going to have your minus h bar squared over 2m second derivative, like that. So this will be equal to the following integral. First off, we can pull these out of the integral because they're just constants. So that's, let me write this a little nicer. So we have the complex conjugate of f, and then the second derivative acting on g, which is just this. Now this is just begging to be integrated by parts. Just to remind you, uv minus the integral of v du is the formula we're going to be using. We'll let u equal f of x and du equal df dx, like such, dx, and then dv you're going to want to equal this derivative, because we're going to integrate that, and now you're going from a second derivative to just a first derivative when we integrate both sides. Okay? Okay, so let's go ahead and plug this in. We have minus h bar squared over 2m. This is out front still. And then we have uv. So we have, I feel like my mic is a bit close, but I'm also not talking super loud. U times v, and this will be evaluated at our bounds, minus the integral with the same bounds of v du. Okay. So we can do this once again, looking at this integral. And you can let u equal this, which tells you that du equals, now it's a second derivative. So now we're taking a derivative with respect to x. And then dv, well, that'll be just dg dx dx. Forgot a dx there, I think. So then when we integrate this, you get v is just g of x. So we have minus h bar squared over 2m times f star of x dg dx evaluated on these bounds minus the integral, and then we just integrated this by parts again. So we're going to have u times v. So once again, these will be evaluated on these bounds minus, so there's already a minus here, so the other minus will make this positive. Of v du. Now remember that these functions are in Hilbert space, so this needs to go to 0 at the plus and minus infinity. So this whole term needs to go to 0. And a similar argument can be made here. This also has to go to 0 at plus or minus infinity, because they're in Hilbert space and they have to be square integrable. So then you just have minus h bar squared 2m, this integral which is just this inner product. I should specify this is just do it like this. So this term is also Hermitian, and since each term, the v of x and this term, are both Hermitian, then from part A we know that a sum of the two Hermitian operators is also Hermitian. So hopefully that makes sense on how we approach this problem. If it did help you, I'd really appreciate it if you'd leave a like and if you would subscribe to my channel. And I'll be sure to post more solutions soon.